Okay, everyone. Good to see you back for the second seminar of the day of the Institute of Physics in Opava. It is my great pleasure indeed to introduce Alexandros Karam. Alexandros was born in Athens, in Greece, and he studied physics at the University of Ioannina. It's my city. He completed his PhD studies in 2018. And since October of 2018, if I remember correctly, Alexandra?
December.
September?
December.
December.
Yeah.
December of 2018, he has been working in Estonia, in Tallinn, in the National Institute of Chemical Physics and Biophysics. His research interests include scaling invariant extensions of the Standard Model, dark matter, modified gravity, inflation, primordial black holes, gravitational waves, you name it. So today, he will talk to us about aspects of Palatini inflation and quintessence. So, Alex.
Thank you, Thomas. Also, I would also like to thank the organizers for inviting me to this seminar series. Okay, I wanted to do a brief introduction about myself, but Thomas said everything. So I was born in Athens. Then I moved to Ioannina to study physics, where I also got my PhD. And then I came here to Tallinn. So since I came here, I have been working mostly on cosmic inflation, which will be the main topic of today's talk. Unfortunately, there will be some overlap with Yannis's talk, since we are both working on inflation, but I will focus on different papers than Yannis. So, as you know, the theory of cosmic inflation was originally proposed as a solution to the flatness and horizon problems. But as it turns out, inflation also explains how quantum fluctuations in space-time were magnified to cosmic size and became the seeds for the growth of structure in the universe. The simplest theory of inflation assumes the existence of one real scalar field phi, which is minimally coupled to gravity, has a canonical kinetic term, and is governed by a potential V. The energy density of this field acted as a cosmological constant and led to the exponential expansion known as inflation. Now, these are the Friedman equations, which describe the expansion of the universe, where h is the Hubble constant or Hubble parameter, and a is the scale factor. A dot here is the differentiation with respect to cosmic time. And this is the Klein-Gordon equation, which describes the dynamics of the scalar field phi, which is the inflation field. Now, inflation is usually studied with the help of the so-called slow roll approximation. In this approximation, the field slowly rolls down the potential so that its potential energy dominates over the kinetic energy. While this condition must also hold so that horizon and flatness problems can be solved. Now, this is the first Hubble slow roll parameter. It's defined like this. And it is small during inflation, but becomes exactly unity at the end of inflation when the acceleration of the scale factor goes to 0. And this is the second Hubble slow roll parameter. Now, in the slow roll approximation, the equations of motion take this simpler form. And it's much easier to analyze. Now, the shape of the potential is encoded in the so-called potential slow roll parameters, the first two of which are these ones, epsilon v and eta v. This one contains the first derivative of the potential, this contains the second derivative. One can write a whole series of potential slow roll parameters with higher derivatives of the potential. But as you go up the ladder of these potential slow roll parameters, they will be generally smaller. And this is a general shape of a potential that can provide successful inflation. So inflation starts here. The field slowly rolls down. Inflation ends here. And then the inflaton field oscillates around the minimum of the potential and decays to other particles most likely the standard model particles, in a process called reheating. Now, these are the observables of inflation. So when someone builds a model, there are some constraints that need to be satisfied. One of them is the amplitude of the scalar power spectrum, which has this value. And it's related to the potential and the potential slow roll parameter from this formula. So whenever one builds an inflationary model, this number has to be satisfied. Then we have the scalar spectral tilt, NS, which is given in the first approximation in terms of the potential slow roll parameters by this formula. And then we have the tensor power spectrum, and the ratio of these two gives us the tensor to scalar ratio. Now, the variation of the field during inflation is related to the so-called number of V-folds, which describe how much of exponential expansion there was during inflation. And it has to be between 50 and 60 for the horizon and flatness problems to be solved. Now, in this paper, back in 2017, with Thomas and Professor Tamvakis, we computed the inflationary observables up to third order in the slow roll expansion. This is only the first order I mentioned here. And these are the results we obtained after some lengthy computations. So this is the first order result, and then until the end of this line is the second order result for NS, and all these lines is the third order. So these potential slow roll parameters are higher order parameters, and this alpha here is just a numerical constant. And this is the result we obtained for the tensor to scalar ratio. So this is the first order result, and then we have the second order until here, and then the third order result. Now, you may ask why we did this, and the answer is that future experiments will be able to measure the tensor to scalar ratio with an accuracy of up to 10 to the minus 4. So it's really important to have also accurate theoretical analytic results. Now, let's see an example. This is the simplest potential what one can write. It's a monomial with a power of phi. And it's easy to compute the first slow roll parameters, epsilon and eta, in terms of the field phi. Then, using that in the first order slow roll approximation, the epsilon Hubble parameter is approximately equal to the potential epsilon, and the end of inflation occurs at when epsilon becomes unity. We can easily obtain the field value at the end of inflation. Then, using that, we can compute the integral for the number of V-folds in terms of the value of the field at the beginning of inflation. And then this can be solved in terms of phi star and plugged back into these expressions for epsilon and eta. And therefore, we can obtain the observables in terms just of the number of V-folds. So for quadratic inflation, given by this very simple potential, we obtain that NS is 0.97 and R is 0.13. As we will see next, this value is excluded. And similarly for the quartic model, we obtain NS 0.95, which is excluded, and R 0.26. So both of these very, very simple potentials are now excluded, as we will see. Now, another very simple and perhaps the most famous inflationary model is that of Starobinsky, who extended the Einstein-Hilbert action with an R² term. So there is no potential, but there is this gravitational correction. Now this this model belongs to the general class of FR theories, which can be written in this form with the help of an auxiliary field chi. Now, after value scaling of the metric and the field definition, we can bring this action in the known form with a potential V, where the field now is minimally coupled to gravity and has a canonical kinetic term. Now, in general, the potential is given by this formula. And this is the new field, the canonicalized field in terms of the auxiliary field. So for the Starobinsky model, we find the famous Starobinsky potential. And for 6 defaults, NS turns out to be 0.9666. And the tensor to scalar ratio is 0.00333, etc. And this is the plot from Planck 2018, which shows the constraints in the NS versus R plane. And this color is the latest constraints. So anything outside of this contour is excluded. So as you can see, quadratic inflation, which is here, is excluded. Quartic inflation is around up here. So it's very, very, very excluded. Linear inflation is here. So now it has been marginally excluded as well. But the Starobinsky model lies here, which is well within the allowed region. But as I said before, in the future, this contour will shrink a lot, since we'll be able to constrain R up to 10 to the minus 4. So as you can see, the Starobinsky model is perhaps the most successful, even 40 years after it was suggested. And because of that, recently it has been, there have been many papers where the Starobinsky model has been combined with other famous inflationary models, such as Higgs inflation. But in these models, since there is now an auxiliary field that is used to parameterize the R² term, plus there is another field, for example, the Higgs field, the resulting model is two-field, which is generally complicated to analyze. So what we will discuss in the following is the differences between the metric and Palatini formulation. Because once one tries to modify the theory of gravity, one has to decide in which formulation to work, because there are differences. So in the metric formulation, the metric is the only dynamical degree of freedom, and the connection has to be the Levi-Civita. While in the Palatini formulation, both the metric and the connection are independent dynamical degrees of freedom, and one has to vary the action with respect to both of them. Now, for a theory, for an action which is linear in R, and the field is minimally coupled to gravity, the two formulations give the same results. However, when the field is non-minimally coupled, and there are higher order terms in terms of the rich scalar, then differences arise. So let's start with some general scalar tensor theory. So no higher order gravitational terms, just a scalar field, which is in general non-minimally coupled to gravity, and it in general has a non-canonical kinetic term. Now, variation with respect to the connection gives this relation, where kappa is 1 in metric. So this does not exist in metric, but it is 0 in Palatini. So this is the new term that arises in Palatini. Now, performing a Weyl rescaling, a Weyl transformation, this is how the the metric transforms. And this is how the Ricci scalar transforms. So as you can see, all of this term is not present in the Palatini formulation. And Ricci scalar is just rescaled by this non-minimal coupling. So in the Einstein frame, the action takes this form, where the potential now is divided by the conformal factor a squared, and there is a non-canonical kinetic term, which contains this piece, which again is multiplied by kappa, which differentiates between the two formulations. Now, if we canonicalize the field via field redefinition, we can plug it back in and arrive at this minimal action, which is easy to analyze in terms of inflation. And as you can see again, the difference between the two formulations arises here. So because of this kappa, because of this difference in the field definition, if you start with the same in principle theory, and you study it both in metric and Palatini, you will find different results. So one of the most famous inflationary models, along with Starobinsky, is non-minimal Higgs inflation, which is given by this quartic potential. And this is the non-minimal coupling function. And it's assumed to have a canonical kinetic term. Note that in most of the slides, I am assuming a notation where m blanc is 1, m blanc square is 1. Now, if we perform a field redefinition in metric, we obtain in the large field value and in the large field limit this approximate relation between the canonical and non-canonical field. Whereas in Palatini, the field redefinition is exact. This is obtained from this equation here. So if we plug this back into the Einstein frame potential, we find this potential for the metric formalism, which is 1 minus exponential of this, all squared. While in Palatini, it becomes hyperbolic tangent to the fourth. And also notice that the square root of psi, the non-minimal coupling, multiplies the field here. So from these potentials, one can calculate the inflationary observables. And as you can see, NS is practically the same in the two formulations. There's only a correction that arises at second order in the number of efforts. So it's a very small difference. But the tensor scalar ratio is quite different. Here it is 12 over n squared. So for 60 efforts is around 10 to the minus 3. When in Palatini, it's 2 over psi n squared. And we will see now what value psi can take. So the amplitude, which if you remember, the amplitude of the scalar power spectrum, if you remember its value is 2.1 times 10 to the minus 10. So this has to be 10 to the minus 10. And assuming Higgs inflation, lambda is taken usually to be 0.1. So for 60 volts, in metric, psi has to be around 10 to the 4 in order to obtain the correct number here. While in Palatini, because there's a different dependence on psi, it has to be 10 to the 9. So from 10 to the 4 in metric, now in Palatini, it has to be 10 to the 9. And because psi enters the formula here for the tensor for the tensor to scalar ratio, since it is 10 to the 9 and it multiplies here a number of 60 squared efforts, we obtain a tensor scalar ratio of the order of 10 to the minus 12 to 10 to the minus 13, which is bad because this value will never be explored by experiments in the next 50 years at least. So indeed, the value of the tensor scalar ratio is smaller in Palatini, but it's so small that we cannot hope to observe it. While this value, 10 to the minus 3, will be available to experiments in the next few years. So we may be able to know if Starobinsky or Higgs inflation, non-minimal Higgs inflation, if these models are the true models of inflation. Now, in this paper, with Sotirios Karamitsos and Margus Sal, we, among other things, we found that in some general models, if the value of psi is smaller than this value, then the metric and Palatini, then the predictions of the model in both metric and Palatini are the same. So they're not experimentally indistinguishable. But if psi is larger than this value, then there are differences. Similarly, in this paper with Laur Yarv, Alexander Kozak, Angelos Likas, Antonio Racciopi, and Margus Sal, among other things, we saw that choosing the model functions of a theory in this particular way, the inflationary observables are actually the same. So in general, in a scalar tensor theory, starting from the same model, the inflationary observables are different, but there are actually a few examples for which NS and R have the same values, which is interesting. Now, in this paper, with Yannis, Angelos Likas, and Thomas, we examined this theory, which is a scalar tensor theory of gravity, with an addition of a non-minimal derivative coupling of this form. Now, this term arises in many supergravity theories, and it's quite natural to write since it does not introduce any new degrees of freedom apart from the graviton and the field, so no new degrees of freedom. Now, usually this parameter m is taken to be constant, but we took it to be field dependent, to be as general as possible. Then, after this formal transformation, one can write the Einstein action in this form, where this quartic kinetic term arises. And the potential has the usual form like in scalar tensor theories. But this function here in front of the kinetic term obtains this correction, which depends on the potential, and this function, this new function of the non-minimal derivative coupling. So in this paper, we examined a few examples, and perhaps the most interesting was this one, where we took this parameter to be proportional to phi squared over some constant m0 squared. And we saw how the inflationary observables change. So what we saw was that the amplitude of the scalar power spectrum receives this correction here, this term, this is the new term, which means that psi does not have to be that big anymore. It doesn't have to be 10 to the 9 as before, but we can fix m0 to some value, and then psi would be free. And then ns changes like this, but as I told you before, this correction is not significant. It's this value that plays most of the role. And this is how the tensor scalar ratio changes. Sorry. Now, because of that, because we can fix m0 at some value to satisfy the constraint on AS, psi does not have to be 10 to the 9, but it can actually be much smaller, which means that since we have a smaller psi now, the tensor scalar ratio value can grow it can go up from 10 to the minus 12, 10 to the minus 13, that it was before in the usual Palatini Higgs inflation, to values up to 10 to the minus 3 almost, meaning that it could be within experimental observability in the future. So if this model is true in the Palatini formulation, then we could see it in the near future. Now, in these two papers, back from 2018, we studied Palatini inflation with an R-squared term. So this is the general action, and we have added an alpha R-squared term, which is a scale invariant term, and it's very natural to write, like Starobinsky did. Now, if we introduce an auxiliary field and rescale the metric, we arrive at this action, where the potential now has this form. So what's interesting now is that in the Palatini formulation, because of the way the real scalar transforms, no kinetic term has been generated for the auxiliary field chi, which is called scalar in the metric formalism, and it is dynamical there. So as we will see, the equation of motion of chi, because it does not have a kinetic term, it reduces just to a constraint. This means that eventually the theory is single field, and the only propagating degree of freedom is phi, which we identify as the inflaton. So this is the constraint equation of chi, meaning that we can solve it if we vary the action with respect to it, then we can solve it in terms of the other field, and then we can plug it in back into the action and arrive at this form for the action, which, as you can see, contains a non-canonical kinetic term, a higher order kinetic term, and a modified potential, which is the usual Einstein frame potential divided by 1 plus 8 alpha u bar. And then we can also canonicalize the field so that we make this kinetic term canonical and study inflation using the usual tools. So this is the final action with this Einstein frame potential. And as you can see, regardless of the shape of the potential, the R-squared term decreases the height of the effective potential because of this parameter alpha entering in front of R-squared. Also, for large values of phi, all of this tends to a plateau with value in blank to the 4/8 alpha. So whatever potential you choose, for large values of phi, it will be a plateau, which is good for inflation. And we also need to take into account this field definition for the field. So now the equations of motion get modified in this way, since we have the higher kinetic term, and there is a dependence on alpha. This is, again, the first Hablus-Laurent parameter, which is less than 1 during inflation, and it receives this correction. Now, what's interesting is that it turns out that the amplitude of the scalar perturbations and the scalar tilt become unaffected by this alpha R-squared term. They don't change with respect to their values without the R-squared term. But the tensor to scalar ratio does get modified in this way, meaning that the value of the tensor to scalar ratio in the model without the R-squared term is now divided by 1 plus 8 alpha u bar, which can also be written in this way, since we know the value of AS. All of this shows that as alpha grows, and as Yannis told you so many times, the value of the tensor to scalar ratio goes down. Therefore, models that were excluded because they had a too large tensor-scalar ratio can now be brought back into agreement with observations. So that's the good thing. However, since, as I told you before, the sensitivity of the future experiments is expected to be around 10 to the minus 4, and it will be very hard in the future to go below that. Alpha, this means that generally alpha has to be less than 10 to the 10 if we want the model to be experimentally verified, to be falsifiable in the future. Otherwise, of course, alpha can be larger, but then the tensor-scalar ratio will be too small to be detected ever. So in this paper, among other things, we studied a very, very simple inflationary potential, which is just a quadratic. It is minimally coupled. There's no minimal coupling. It has a canonical kinetic term. What's very nice about this model is that the field redefinition can be solved analytically. And then we obtain this nice potential. And as you can see in this plot, starting from a quadratic potential, as the value of alpha grows, then the potential gets flattened and we get plateaus, and also the height of it goes down. So inflation takes place in lower energy scales, and also the form of the potential is more flat, meaning that the tensor-scalar ratio can be smaller. And you can also see that in this analytic expression. Now, m squared, the mass here, is fixed by the amplitude to be around 10 to the minus 5, meaning that for alpha above around 10 to the 7 to 10 to the 8, we can see that the tensor-scalar ratio can go down. This value here is 0.13, which is excluded. But again, as if alpha is around 10 to the 8 and above, then the tensor-scalar ratio can be smaller. Therefore, this model can be in agreement with observations. Not verified, but in agreement. Now, in this paper with Emily and Hardy, Emily Tomberg and Hardy Vermain, my colleagues here in Tallinn, among other things, we saw that unitarity considerations actually constrain the value of alpha to be less than around 10 to the 20. So we have, in a sense, we have a lower limit from this if we wish to save this model, and we have an upper limit from unitarity. Now, we also applied this Palatini R-squared formulation to a few more models, but Yanis talked to you about this one, so I think I will just skip it. But the main point is that in this model, we can have the dynamical generation of the Planck scale through the vacuum expectation of a field phi, which is non-minimally coupled to gravity, because at the minimum, this field can generate the Planck scale. And there were two cases. One of them corresponded to quadratic gravity, and the other one was interpolating between linear and quadratic gravity, depending on the value of the non-minimal coupling. Both of these limits, however, both the linear and the quadratic limit are excluded. However, when the potential gets modified due to the R-squared term, then both of these potentials, the linear and the quadratic, get flattened, and the tensor-scalar ratio value changes, and it can be made to agree with observations again. So this was the main point of this paper. Now, okay, you may say we have some theories of inflation that seem successful. So inflation is a period of accelerated expansion, But what about the accelerated expansion that we live in now? That is dark energy. Is there a way to describe dark energy through a dynamical field? And if yes, can this be combined with the theory of inflation, since that is also a period of accelerated expansion? And the answer is maybe. If we have a potential that looks like this, then the same field can actually play the role of the inflaton and then become dark energy. So the field starts here, it slow rolls in order to produce the inflationary observables. Then inflation ends here. There is a period of kination where the kinetic energy dominates over the potential. Then there is the usual hot Big Bang model. So there is a period of radiation domination. Then there is a period of matter domination. And after that, we basically have slow roll inflation again, which leads to what we observe as dark energy. And the potential at during this era has the value of the cosmological constant. Now, in this picture, the equation of state parameter, which is defined as the pressure over the energy density, has this general form. It starts from -1 during inflation. As you can see, when the potential dominates, then these terms go away and it's -1. Then during kination, the opposite happens. This term dominates and it's +1. And then we have this, the radiation and matter eras. And after that, we have dark energy when W becomes -1 again. Yes, there was another plot here. This one. Okay. Now this is the energy density. It is proportional to the Hubble parameter during inflation, which is proportional to square root of the potential. Then it scales as the scale factor to the -6 during kination, as the scale factor to the -4 during radiation, as the scale factor to the -3 during matter domination, and now it should be proportional to the cosmological constant. So what is really challenging is to construct a model like this. If one wants to describe all of the universe's evolution with one single field. And the challenge is to satisfy all the cosmological constraints. So we try to do that in this paper with Kostas Dimopoulos and Samuel Sanchez-Lopez from Lancaster and Emily Tomberg, my colleague here. So what we did was that we consider an action of this form where this function f here contains an R² term, and also the field is non-minimally coupled to gravity in the Palatini formulation. Another ingredient that we had to introduce was the running of Xi with respect to energy in order to satisfy the constraints. And what is nice about this model is this very simple form for the potential. It's a negative exponential, which to my opinion is very natural to write down. And it arises in many superstring theories. Now, after doing all of the above that I discussed, in the Einstein frame, the potential takes this form. And if you plot it, it looks like this. So in principle, it could do both inflation and quintessence. So I won't go through this, but trust me that we satisfied all of the constraints with this model, which are all of this. And eventually we found a few benchmark points that work and satisfy all of the constraints. So the model can do successful inflation, then evade all the Big Bang Theory model, all the Big Bang Theory constraints, and lead to the values that give us dark energy today. So in conclusion, if one adds an alpha squared term in the metric formalism, the model leads to two-field inflation, which is quite difficult to analyze. However, in Palatini, it leads to single-field inflation. The difference is that the effective potential is asymptotically flat and has a lower value. And as we saw, as the value of alpha grows, the value of the tensor scalar ratio becomes smaller, meaning that models that were previously excluded can now be made into agreement with observations. However, the values of the amplitude and NS do not change. And what's also interesting is that this flattening effect can be used to construct models of quintessential inflation, therefore have a single field that can do both works, can describe both inflation and dark energy. We also saw that a model we studied with non-minimal derivative coupling leads to an action which is similar to Palatini R squared. However, there, due to the different form of the field definition, also the different form of the potential, the value of the tensor scalar ratio tends to increase. Thank you.